Hello everyone. Today, let's continue with elementary number theory. First of all, let me introduce a theorem called Bezout theorem. Bezout theorem says let a and b be two positive integers with GCD of AB equal to D. Then D can always be written as D equal to S times A plus T times B, with S and T are integers. Bezout theorem says let A and B be two positive integers with the GCD of AB equal to D. Then D can always be written as D equal to S times A plus T times B, with S and T are integers. This is called a linear combination of A and B. This is called a linear combination of A and B. With integer coefficients. So Bezout theorem says if D is the GCD of AB, then I can write D in terms of A and B. I can write D in terms of A and B with integer coefficients. If D is the GCD of AB, I can write D as a linear combination of A and B with integer coefficients. That's what Bezout theorem says. Next, let's look at some simple examples. Let's look at an example related to Bezout theorem. For each of the following pairs of integers, write the GCD write their greatest common divisor as a linear combination of the given numbers. First example, 13 and 61. Here we try to write their GCD as a linear combination of these two numbers. First of all, what's their GCD? In order to find the GCD, let's use Euclidean algorithm. So GCD of 13 and 61 By Euclidean algorithm, we take larger number divided by the smaller number. 61 divided by 13. 13 goes to 61 4 times. 4 times 13 is 52. Remainder is 9. So we keep the divisor the same. Keep 13 the same. Keep divisor the same. Replace the dividend with the remainder. Replace the dividend with the remainder. Then keep going. Take 13 divided by 9. 9 goes into 13 one time. 1 times 9 is 9. Remainder is 4. Then keep the divisor the same. Replace the dividend with the remainder. Then keep going. Take 9 divided by 4. Take larger number divided by smaller number. 4 goes to 9 2 times. 2 times 4 is 8. Remainder is 1. So keep the divisor the same. Replace the dividend with number 1 with the remainder. Then keep dividing. Take larger number divided by smaller number. 4 divided by 1. 1 goes into 4 4 times. 4 times 1 is 4. Remainder is 0. Then keep the divisor the same. Replace the dividend with the remainder. GCD of 0 and 1 is 1. That's the GCD. Then by Bezout theorem, Bezout theorem says we can always run a GCD in terms of the original numbers. We can always run a GCD as a linear combination of the original given numbers. So by Bezout theorem, we know that we can write 1 as a linear combination of 13 and 61. Bezout theorem says we can write 1 as a linear combination of 13 and 61. But how can we do that? This part is called the Euclidean algorithm. Next, we try to write 1 as a linear combination of 13 and 61. Let me show you one way to do that. This technique is called the extended Euclidean algorithm. This technique is called the extended Euclidean algorithm. This technique is called extended Euclidean algorithm. Let me show you here. First step, convert each division into an equation. Convert each division into an equation. Now first division here. 61 divided by 13. 13 goes to 61 4 times. Remainder is 9. This equation can be written as 61 equal to 4 times 13 plus 9. 61 equal to 4 times 13 plus 9. Let me put it here. That's the first equation. 61 equal to 4 times 13 plus 9. Next equation. 13 equal to 1 times 9 plus 4. 13 equal to 1 times 9 plus 4. Next equation, number 9. 9 equal to 2 times 4 plus 1. Next equation, number 4. 4 equal to 4 times 1 plus 0. So, rewrite each division as an equation. Rewrite each equation as a division. 61 equal to 4 times 13 plus 9. Usually put a divisor in the parentheses. Put a divisor in the parentheses. Put a divisor in the parentheses. So let's copy the equation here. We convert, first of all, for extended Euclidean algorithm, we first of all convert each division into an equation. Remove the row that ends with a 0. We don't need the row that ends with a 0. Remove the row that ends with a 0. We don't need this row. Remove the row that ends with a 0. So convert each division into an equation. Then remove the row that ends with remove the last row that ends with a 0. Remove the last row which ends with a 0. Next, on each row here, isolate the remainder. Isolate the remainder. Isolate the remainder. 1 equal to 9 minus 2 times 4. Bring 2 times 4 over. 1 equal to 9 minus 2 times 4. Isolate 4. 4 equal to 13 minus 1 times 9. Isolate 9. 9 equal to 61 minus 4 times 13. On each equation, get a remainder by itself. On each equation, get a remainder by itself. Now, start from the last equation. Start from the last equation. 1 equal to 9 minus 2 times 4. Start from last equation. In this equation, replace 4 with the previous row because the previous row equal to 4. Replace number 4 with the previous row. Replace 4 with 13 minus 1 times 9. Then distribute 2. I get 2 times 13. Negative 2 times negative 1 is positive 2. I get 9 minus 2 times 13 plus 2 times 9. Here we have 1 9 plus 2 9. Here we have 1 9 plus 2 9. If I combine like terms, that's 3 times 9. I have 1 9 plus 2 9. If I combine like terms, I have 3 times 9 minus 2 times 13. Next, replace number 9. Replace number 9 with the previous row. 9 is 61 minus 4 times 13. Replace number 9 with the previous row. Minus 2 times 13. That stays the same. Minus 2 times 13. That stays the same. Then distribute 3. I get 3 times 61 minus 12 times 13. Three times 61 minus 3 times 4 is 12. Minus 12 times 13. Minus 2 times 13. Combine like terms. Negative 12 times 13 plus negative 2 times 13. That's negative 14 times 13. If I combine like terms, if I treat 13 as x. Then I write number 1. I write the GCD. GCD is number 1. I write number 1 as a linear combination of 13 and 61. Here I write number 1, the GCD, as a linear combination of 13 and 61. This technique is called the extended Euclidean algorithm. Part B. Let's try a different pair of numbers. 14 and 106. We try to write their GCD as a linear combination of 14 and 106. We try to write their GCD as a linear combination of 14 and 106. So, let's first of all use Euclidean algorithm to find the GCD. Let's first of all use Euclidean algorithm to find the GCD. For GCD of 14 and 106, first of all do long division. 106 divided by 14. 14 goes into 106 7 times. 7 times 14 is 98. Remainder is A. So replace the larger number, keep the divisor the same. Replace the larger number with the remainder. Then take larger number, divide by smaller number. 14 divided by 8. 8 goes into 14 one time. 1 times 8 is 8. Remainder is 6. So replace. Keep the divisor the same. Replace the larger number with the remainder. Then keep doing long division. Take the larger number, divide by the smaller number. 8 divided by 6. 6 goes into 8 one time. 1 times 6 is 6. Remainder is 2. Replace the larger number with the remainder. Then keep doing long division. Take 6 divided by 2. Number 2 goes into 6 3 times. 3 times 2 is 6. 6 minus 6 is 0. Then let the divisor stays the same. Replace the dividend with a remainder. GCD of 0 and 2 is 2. GCD of 0 and 2 is 2. Next, we try to rewrite each division as an equation. Do it in order. It must be in this order. Do it in this order. 106 equal to 7 times 14 plus a. 106 equal to 7 times 14 plus a. 14 equal to 1 times a plus 6. Number a equal to 1 times 6 plus 2. Number a equal to 1 times 6 plus 2. Number 6 equal to 3 times 2 plus 0. Number 6 equal to 3 times 2 plus 0. We remove the row that ends with a 0. Remove the last row that ends with a 0. We don't need this row. Remove the last row that ends with 0. Start from the non-zero rows. Isolate the remainder. Get the remainder by itself. Isolate each remainder. Get the remainder by itself. Get 2 by itself. 2 equal to a minus 1 times 6. 6 equal to 14 minus 1 times a. First row. Number a equal to 106 minus 7 times 14. Then we're doing substitution. Work backwards. Start from the last equation. We are doing substitution. Last row. Start from last row. Number 2 equal to a minus 1 times 6. Replace number 6 with the previous row. Number 6 is 14 minus 1 times a. Number 6 is 14 minus 1 times a. Distribute negative 1. We get negative 1 times 14. Negative 1 times negative 1 is positive 1. Negative 1 times negative 1 is positive 1. Then if I combine like terms, 1a plus another 1a is 2a. 1a plus another 1a is 2a. Minus 1 times 14. Next, replace number a with the previous row. Replace number a with the previous row. Number a is 106 minus 7 times 14 minus 1 times 14. Minus 1 times 14 stays the same. Replace number a with the previous row. Replace number a with the previous row. Then simplify. If I distribute 2, I get 2 times 106 minus 2 times 7 is 14. Minus 14 times 14 minus 1 times 14. Then combine like terms. Negative 14 plus negative 1 is negative 15 times 14. So 2 equal to 2 times 106 minus 15 times 14. Here I write the GCD. GCD is 2. I know that GCD is a linear combination of 14 and 106. Here I write number 2. The GCD is a linear combination of 14 and 106. Next example. $180 and 55. So we try to write that GCD is a linear combination of 180 and 55. We try to write that GCD is a linear combination of 180 and 55. So first step, use Euclidean algorithm, find their GCD. First step, use Euclidean algorithm, find their GCD. GCD of 180 and 55. Do long division. 180 divided by 55. 55 goes into 180 3 times. 3 times 55 is 165. Remainder is 15. So replace the dividend, the larger number, with the remainder. The divisor stays the same. Then use larger number divided by the smaller number. Take 55 divided by 15. 15 goes into 55 3 times. 3 times 15 is 45. 55 minus 45, remainder is 10. So replace the dividend with a remainder. Keep the divisor the same. Next, keep going. Take larger number, divide by smaller number. Take 15, divide by 10. 10 goes to 15 one time. 1 times 10 is 10. Remainder is 5. So replace the larger number with a remainder. Replace 15 with a remainder. Keep the divisor the same. Then do long division. Take 10, divide by 5. 5 goes to 10 2 times. 2 times 5 is 10. Remainder is 0. So keep the divisor the same. Replace the dividend with a remainder. GCD of 5 and 0 is 5. That's the GCD. Next, by Bezout's theorem says we can write 5 in terms of these two numbers. I can write 5 as a linear combination of these two numbers. That's what Bezout's theorem says. So next, let's try to write 5 in terms of these two numbers using extended Euclidean algorithm. First step, convert each division as an equation. Convert each division into an equation. First division, 180 equal to 3 times 55 plus 15. Next equation, 55 equal to 3 times 15 plus 10. Next equation, 15 equal to 1 times 10 plus 5. Next equation, 10 equal to 2 times 5 plus 10 plus 0. 10 equal to 2 times 5 plus 0. Then we remove the row that ends with a 0. Remove the row that ends with a 0. Start from, for each row here, get a remainder by itself. For each row here, get a remainder by itself. 4 equal to 15 minus 1 times 10. On each row, get a remainder by itself. 10 equal to 55 minus 3 times 15. 15 equal to 180 minus 3 times 55. Next, try to substitute. Work backward and substitute. Start from the last row. 4 equal to 15 minus 1 times 10. 4 equal to 15 minus 1 times 10. Replace number 10 with the previous row. Number 10 is 55 minus 3 times 15. Replace number 10 with the previous row. Then simplify. If I distribute 1, I get 1 times 55 plus 3 times 15. Then if I combine like terms, 115 plus 315 is 415. 115 plus 315 is 415. That's 4 times 15 minus 1 times 55. Four equal to 4 times 15 minus 1 times 55. Next, go to the previous row. Replace 15. Replace 15 with 180 minus 3 times 55. Replace 15 with 180 minus 3 times 55. One minus 15 stays. 1 minus 55 stays the same. Distribute 4, we get 4 times 180 minus 12 times 55 minus 1 times 55. Then combine like terms. Negative 12 plus negative 1 is negative 13 times 55. Here I write the GCD, which is 5. I write the GCD in terms of, I write GCD as a linear combination of 180 and 55. Here I write the GCD as a linear combination of 180 and 55. Next, let me show you modular arithmetic. Modular arithmetic. Let a, b, and m be integers. With m greater than 0. If m divides a minus b, if m divides a minus b, then we say a is congruent to b ma m. A is congruent to b ma m. If m divides a minus b, then we say a is congruent to b ma m, denoted by a congruent to b ma m. This 3 bar means congruence, two numbers congruence. A congruent to b ma m. So if a m divides a minus b, then we say a congruent to b ma m. Keep this in mind. M divides a minus b. That's equivalent to a congruent to b ma m. M divides a minus b. That's equivalent to a congruent to b ma m. Keep this in mind. Next, let's do a simple example. For each of the following statements, determine its true value. For each of the following statements, determine its true value. First statement, if I say 7 congruent to 19 mod 4, is this statement true? Is this a true statement? We try to verify. Use this definition, try to verify. This is A, this is B, this is M. We try to verify. Does M divide A minus B? Does 4 divide 7 minus 19? Does 4 divide 7 minus 19? Does 4 divide negative 12? We know that 4 times negative 3 is negative 12. We know 4 times negative 3 is negative 12. So this statement is true. If this statement is true, this statement is also true. So this is a true statement. Because 4 divides 7 minus 19. That's equivalent to say 7 congruent to 19 mod 4. Next. 6 congruent to 32 mod 3. Is this a true statement? 6 congruent to 32 mod 3. Is this a true statement? Let's verify this. Here, first number 6 is A. That's A, that's B, that's M. A, B, M. That's A, that's B, that's M. Let's check. Does M divide A minus B? Does 3 divide 6 minus 32? 6 minus 32. 6 minus 32 is negative 26. Does 3 divide negative 26? Can we find some number that's 3 times this number equal to negative 26? We know 26 divided by 3 is not a whole number. So we cannot find such number. We cannot find such integer here. Because 26 divided by 3 is not a whole number. So we cannot find any whole number here to make 3 times that whole number equal to 26. So this is a false statement. If this is a false statement, this is also false because they are equivalent. If this is false, this is also false. Since 3 doesn't divide 6 minus 32, this is a false statement. Next. How about this? Negative 23 congruent to 12 mod 5. Is this a true statement? Negative 23 congruent to 12 mod 5. Is this a true statement? Let's check using this definition. This number is A, that's B, that's M. We try to verify. Does 5 divides negative 23 minus 12? Does 5 divides A minus B? That's A, that's B. Does M divides A minus B? That's A, that's B. Let's verify this statement here. Negative 23 minus 12 is negative 35. Does 5 divides negative 35? Can we find some number? Can we find some number that 5 times this number equal to negative 35? We know that 5 times negative 7 is negative 35. So this is a true statement. If this statement is true, this is also a true statement. Next. Negative 38 congruent to negative 12 mod 7. Is this a true statement? Let's verify using this definition here. Is this a true statement? Let's verify. M divides A minus B. 7 divides negative 38 minus negative 12. Is this true? Negative 38 minus negative 12 is negative 26. Can we find some integer such that 7 times the integer equal to negative 26? we know that 26 divided by 7 is not a whole number. 26 divided by 7 is not a whole number, so we cannot find such integers. 26 divided by 7 is not a whole number, so we cannot find such integers here. This is a false statement. If this is a false statement, this statement is also false. Note: for congruence, keep one idea in mind. Keep one idea in mind. A rough idea about A congruent to B mod M is that A and B have the same remainder when they are divided by M. If A congruent to B, then A and B have the same remainder when they are divided by M. We can check here. In the first example, 7 and 19 they are congruence. This is a true statement. 7 and 19 they are congruence. If I take 7 divided by 4, what's the remainder? If I take 7 divided by 4, remainder is 3. If I take 19 divided by 4, what's the remainder? Four goes to 19 4 times. 4 times 4 is 16, remainder is 3. So they both have remainder 3. 7 and 19, when they are divided by 4, they both have remainder 3. So they are congruence. Now let's check 6 and 32. If they are not congruence, that means they have different remainders. If they are not congruence, if this is a false statement, means they are not congruent to each other. That means 6 is not congruent to 32. If they are not congruent, that means the remainder, they must have different remainder when divided by 3. Let's check. If I take 6 divided by 3, what's the remainder? 3 goes into 6 2 times. 2 times 3 is 6, remainder is 0. If I take 32 divided by 3, 3 goes into 32 10 times. 10 times 30 is 3 is 30, remainder is 2. So they have different remainders. They have different remainder when they are divided by 3. So they are not congruent to each other. This is a false statement. Example 3. If I take negative 23 divided by 5, what's the remainder? We must use division algorithm here to find the remainder. Using the equation A equal to QD plus R. Find the quotient first. So A is negative 23. We try to divide this number by 5. A is negative 23. We try to divide this number by 5 and find the remainder. For the quotient, take a negative 23 divided by 5. That's negative 4 and 3/5. If I round to the nearest whole number to the left on the number line, that's negative 5. So Q is negative 5. A equal to QD plus R. A is negative 23. Q is negative 5. D is 5 plus R. Negative 23 equal to 25 plus R. So that's negative 25 plus R. If I add 25 to both sides, R is 2. So remainder is 2. Negative 23 divided by 5, remainder is 2. How about 12? 12 divided by 5, remainder is also 2. Since they have the same remainder, they are congruent to each other. Since they have the same remainder, they are congruent to each other. And example 4. If they are not congruent, this is false statement. If these two numbers they are not congruent to 7, then they must have different remainders. If I take negative 38 divided by 7, a is negative 38, divisor is 7. Take negative 38 divided by 7. Find the quotient first. Quotient is negative 38 divided by 7, which is negative 5 and 3 over 7. For the floor function, round to the nearest whole number to the left, that's negative 6. Then, using this equation, find R. A equal to QD plus R. A is negative 38. Q is negative 6. D is 7 plus R. That's negative 42. If I add 42 to both sides, R is 4. So for negative 38 divided by 7, remainder is 4. How about negative 12? If A is negative 12, we're going to divide by 7. Find Q first. Q is the floor function, negative 12 divided by 7. Negative 12 divided by 7 can be rewritten as negative 1 and 5 over 7. If I take floor function, that's negative 2. Then use this equation, solve for R. A equal to QD plus R. A is negative 12. Q is negative 2. D is 7 plus R. So negative 12 plus negative 14. Negative 12 equal to negative 14 plus R. If I add 14 to both sides, R is 2. So remainder of negative 38 is 4. But remainder of negative 12 is 2. Since they have different remainders, they are not congruent to each other. This is a false statement. So the rough idea for A congruent to B is, if A congruent to B, then A and B has the same remainders when they are divided by M. If they are not congruent, then they have different remainders. That means if they have different remainders, they are not congruent to each other. Next, let's look at a theorem about congruence. Let A, B, C, M be integers with M greater than 0. Let A, B, C, M be integers with M greater than 0. Then we have the following statements. The first statement says, A always congruent to itself, my M. A always congruent to itself, my M. Statement 2 says, if A congruent to B, my M, then B congruent to A, my M. If A congruent to B, my M, then B congruent to A, my M. Next, if A congruent to B, my M, and B congruent to C, my M, then if A congruent to B, B congruent to C, then A congruent to C, my M. Let's prove each of them. Proof from the first statement. How do we prove A congruent to A, my M? How do we prove A congruent to A, my M? Since A minus A is 0, since a minus a is 0, and every number divides 0, since a minus a is 0, and every number m divides 0, then we can say m divides a minus a. Hence, so by definition, a congruent to a by m. Since m divides a minus a, then a congruent to a by m. The definition is m divides a minus b. If and only if that's equivalent to a congruent to b by m. That's the definition here. If m divides a minus a, then a congruent to a by m. That's the proof for the first statement. Second statement. How do we prove second statement? If a congruent to b by m, if a congruent to b by m, then b congruent to a by m. So start from what's given. A, since a congruent to b by m, then that means m divides a minus b. Since a congruent to b by m, then m divides a minus b. Hence, m times the integer k equal to a minus b. Since m divides a minus b, then m times the integer k equal to a minus b, where k is an integer. Then, if I multiply both sides of an equation by -1, if I multiply both sides of an equation by -1, then m times negative k equal to b minus a. If I multiply both sides by -1, then m times negative k equal to b minus a. And we know that since k is an integer, negative k is also an integer. Since k is an integer, negative k is also an integer. So m divides b minus a. Since m divides b minus a, then by definition, since m divides b minus a, then b congruent to a by m. So b congruent to a by m. That's the proof of the second statement. The third statement. The third statement says, if a congruent to b by m, if a congruent to b by m, b congruent to c by m, then a congruent to c by m. So if a congruent to b, b congruent to c, then a congruent to c. We try to prove a congruent to c. So start from what's given. Since a congruent to b by m, then m divides a minus b. So m times the integer k equal to a minus b, where k is an integer. Since b congruent to c by m, Since B congruent to C my M, then M divides B minus C. Since B congruent to C my M, then M divides B minus C. So M, that means M times the integer L equal to B minus C, where L is an integer. Now, we have these two equations here. If I add the equation, what do we get? Mk equal to A minus B. Ml equal to B minus C. If I add the equation, what do I get? If I add the equation, I have Mk plus Ml equal to A minus B plus B minus C. If I add the equation, A minus B plus B minus C. On the left side, I can factor M out. On the left side, I can factor M out. If I factor M out, I get K plus L. On the right side, I can cancel positive negative B. I get A minus C. On the right side, I can cancel positive negative B. I get A minus C. Since K and L, they are both integers. Integer plus integer is integer. Since K times the integer equal to A minus C, that means, so since M times the integer, equal to A minus C, that means M divides A minus C. If M divides A minus C, by its definition, that means A congruent to C my M. That's a proof of statement 3. That's a proof of statement 3. If A congruent to B my M, B congruent to C my M, then A congruent to C my M. That's proof of statement number 3. Next theorem. Let A, B, C, D, and M be integers. If A congruent to B my M, and C congruent to D my M, then we have A plus C congruent to B plus D my M, and we have A times C congruent to B times D my M. If A congruent to B my M and C congruent to D my M, then if I add the left side, AC plus BD. If I add the left side, AC and BD, they are congruent, my M. If I multiply A times C, they're congruent to B times D, my M. If I write it this way, it will be more clear. If I have A congruent to B, my M, C congruent to D, my M. If I add both sides, I have A plus C congruent to B plus D, my M. If I multiply A congruent to B mod M, C congruent to D mod M. If I multiply, I have AC congruent to BD mod M. If I add, I have A plus C congruent to B plus D mod M. If I multiply, I have AC congruent to BD mod M. That's what this theorem says. If A congruent to B mod M, C congruent to D mod M, then A plus C congruent to B plus D mod M, A plus C congruent to B plus D mod M, and AC congruent to BD mod M. AC congruent to BD mod M. So that's what this theorem says. If A and B are congruent, C and D are congruent, I can add left side to the left side and right side to the right side. If A and B are congruent, C and D are congruent, I can add left side to the left side, right side to the right side. If A and B are congruent, C and D are congruent, I can multiply left side to the left side, right side to the right side. So that's what this theorem says. Let's prove it. Let's prove it. So what's given here is A congruent to B mod M, C congruent to D mod M. Let's write down what's given first. Since A congruent to B mod M, then M divides A minus B. So that means M times the integer K equal to A minus B, where K is an integer. If I solve this equation for A, I can write A equal to B plus MK. If I solve this equation for A, I can bring B over. A equal to B plus MK. Similarly, since C congruent to D mod M, then M divides C minus D. Since C congruent to D mod M, then M divides C minus D. So that means M times the integer L congruent to C minus D, where L is an integer. So if I solve this equation for C, C equal to D plus ML. If I solve this equation for C, I bring D over. So C equal to D plus ML. Now we have A, we have C. Let's prove the first statement first. First statement have A plus C. First statement has A plus C. What's A plus C? A plus C equal to B plus MK plus D plus ML. A plus C equal to B plus MK plus D plus ML. That's A, that's C. If I simplify, I can write it as B plus D plus MK plus ML. I can put BD together, put MK and ML together. So on the right side, if I pull out M, I have M times K plus L. Next, I can bring b plus d over, bring b plus d to the left side. I have a plus c minus b plus d equal to m times k plus l. I bring b plus d over. So this is a number, this is a number, and this is an integer. K plus L, since both K and L are integers, K plus L is an integer. K plus L is an integer. Since M times the integer equal to this number, since M times the integer equal to this number, then I can say M divides this number. Since this number equal to M times the integer, I can say M divides this number. So M divides A plus C minus B plus D. Then by its definition, A plus C congruent to B plus D my M. Since M divides this number minus this number, so first number congruent to the second number my M. That's the definition of modular. That's the definition of modular of M. Next, let's try to prove the second statement. This is a proof of the first statement. Next, this is a proof of the first statement. Next, let's try to prove the second statement. For the second statement, I try to multiply AC. For the second statement, I try to multiply AC. A times C. Here, A is B plus MK. C is D plus ML. If I FOIL, I have BD plus BML plus DMK plus M square KL. If I FOIL, I get BD, BML, DMK, M square KL. Then I can bring BD over. If I bring BD over, what's left is these three terms. For these three terms here, I can factor M out. For these three terms, I can factor M out. If I pull M, I get BL plus DK plus MKL. This is the integer. Since this number equal to M times the integer, since this number equal to M times the integer, then I can say M divides AC minus BD. Since this number equal to M times the integer, then I can say M divides AC minus BD. So by its definition, if M divides a number minus a different number, then the first number congruent to the second number my M. If M divides the difference of two numbers, then the first number congruent to the second number my M. So AC congruent to BD my M. That's a proof of the second statement. So that's a proof of the first statement. That's a proof of the second statement. First statement says if A congruent to B and C congruent to D, I can add the left side to the left side and right side to the right side. Second statement says I can multiply left side to the left side and right side to the right side. That's two operations about linear congruence. That's two operations about congruence. Next, let me show you a lemma. Lemma is a simple theorem. Let m be an integer. With m greater than 0. Then km always congruent to 0 mod m. Then km always congruent to 0 mod m. For all integer k. Let m be an integer with m greater than 0. Then km always congruent to 0 mod m for all integer k. Let's prove it. Since k is an integer, then mk is a multiple of m. Since k is an integer, then m times k is a multiple of m. So m divides mk. Since mk can be rewritten as mk minus 0, then I can say m divides mk minus 0. Since mk is the same as mk minus 0, so I can rewrite this as m divides mk minus 0. So by its definition, mk, first number congruent to the second number, congruent to 0, mod m. That's a proof of the lemma. This lemma says any multiple of m always congruent to 0 mod m. Any multiple of m. This lemma says any multiple of m always congruent to 0 mod m. Next lemma. Let a, b, m be integers with m greater than 0 if a congruent to b mod m. Then if a congruent to b mod m, then a congruent to b plus km mod m for all integer k. If a congruent to b mod m, then a congruent to b plus km mod m. This lemma says, if a congruent to b mod m, I can add any multiple of m to one side. The congruence still holds. They are still congruent to each other. If a congruent to b mod m, I can add any multiple of m. I can add any multiple of m to one side. This congruence is still true. They are still congruent to each other. I can add any multiple of m to one side. They still congruent to each other. Let's prove it. Since k is an integer, then by the previous lemma, by the previous lemma. Km congruent to 0 ma m. The previous lemma says any multiple of m congruent to 0 ma m. Hence, 0 congruent to Km ma m. That's one of the theorem we proved earlier today. If A congruent to B, then B congruent to A. That's called symmetric property. If A congruent to B, then B congruent to A. That's called symmetric property. If Km congruent to 0, then 0 congruent to Km. Then, since A congruent to B ma m and 0 congruent to Km ma m, since A congruent to B ma m and 0 congruent to Km ma m, then by this theorem, I'm allowed to add left side to the left side, right side to the right side. Add left side to the left side, I get A. If I add right side to the right side, I get B plus Km ma m. That completes the proof. This theorem says if A congruent to B, I can add any multiple of m to one side of the linear congruence. The congruence is still true. Next theorem. Let A, B, M be integers. With m greater than 0. If A congruent to B ma m, then A raised to power n congruent to B raised to power n ma m for all integer n greater than or equal to 1. For all integer n greater than or equal to 1. How do we prove this theorem? For this theorem, we can try to prove by mathematical induction. We try to prove this statement is true for all integer n greater than or equal to 1. We can try to prove this by mathematical induction. So induction, the basic step. Try to verify that this statement is true when n equal to 1. When n equal to 1, A to the power 1 since A congruent to B ma m, then I can say A raised to power 1 congruent to B raised to power 1 ma m. Since A congruent to B ma m, that's given. Then I can say A raised to power 1 congruent to B raised to power 1 ma m. So the statement an congruent to bn ma m is true when n equal to 1. That's the basic step. Next, the inductive step. Assume this statement is true when n equal to k. So assume a to the power k congruent to b to the power k mod m, where k is an integer greater or equal to 1. Assume this statement is true when n equal to k. This is the induction hypothesis. We try to prove that this statement is also true when n equal to k plus 1. We try to prove that this statement is also true when n equal to k plus 1. Now, we have a to the power k congruent to b to the power k mod m. And by assumption, we know a congruent to b mod m. By the previous theorem, it says, if a congruent to b, c congruent to d, I can multiply left side to the left side and right side to the right side. They are still congruent to each other. So I can multiply left side to the left side, right side to the right side. They are still congruent to each other. If I multiply left side to the right side, I get a to the power of k plus 1. If I multiply right side to the right side, I get b to the power of k plus 1 mod m. So I can say a to the power n congruent to b to the power n. When n equal to k plus 1. When n equal to k plus 1, they are congruent to each other. So that complete the inductive step. That's the proof of this theorem. This theorem says, if a congruent to b, then I can raise both sides to the same power. This theorem says, if a congruent to b, then I can raise both sides to the same power. They are still congruent to each other. If a congruent to b, I can raise both sides to the same power. They still congruent to each other.